Hi everyone, I'm Sumeer from HexLab Stony Brook, and this is a work in collaboration with my mentor Theo and my advisor Michalis Polychronakis. I will be talking about website fingerprinting in IPv6 and does more space lead to less privacy? This is the question that we'll be answering throughout the study. So, as a quick background, as domain name encryption becomes more prevalent, adversaries cannot really rely on plain text DNS queries or plain text domain names in network traffic to fingerprint websites or devices. As a primary fallback, adversaries have started to rely on the destination IP addresses of the servers that users connect to, and this is this has been primarily been explored in IPv4, but IPv6 is still unexplored because, and the reason why we want to explore this in IPv6 is because it's a new ecosystem. We have larger address space, we have an idea of end-to-end connectivity, so it is very timely that we investigate this issue. So, since DNS encryption only hides domain names, website fingerprinting is still possible using other metadata such as packet frequency, packet timings, TLS fingerprints, website oracles, and sequence of IP connection. And among all of these, we choose just the destination IP addresses. And the reason we use this approach or IP based fingerprinting is because it's lightweight, it's computationally efficient, and there has been quite some work in IPv4, and it has proved to give us fairly decent accuracies in IPv4. However, there are some better fingerprinting approaches, such as machine learning, which can promise us even better accuracies. But the goal of this project is to explore the problem rather than achieving high accuracies. So if we see better fingerprinting just on the basis of IP addresses, there is a slightly better chance. There's a chance that machine learning would also perform better. Since IPv6 has a huge address space, there is no need to virtually host domains, which means that there's no need to host multiple domains in a single IP address. And IPv6 promises to restore the idea of end-to-end connectivity, which means that each service or device on the internet should be able to have a unique globally routable address. So some past studies have shown that a majority of IPv6 addresses host a single domain as compared to IPv4. So there's this concern in the community that this may lead to more fingerprinting because now each domain name is more likely to have a unique IP address, which was not the case in IPv4 because of virtual hosting and other technologies such as NAT. According to this context, we formulate the following research questions. We want to know what are the trends of IPv6 adoption in websites. We want to know how effective it is to build IPv6 fingerprints as compared to IPv4. And we want to know that is it even possible to scale this IPv6 fingerprinting to have stable fingerprints. And lastly, we want to see how hosting providers are deploying IPv6 in terms of domain co-location. Our threat model is pretty simple. We assume that there is an on-path observer that is able to see the destination IP addresses of all outgoing packets. And this could be your ISP, censoring middle box, or a network admin. And we also assume that the adversary can capture sequential browsing sessions. We'll come to that later. We assume that all DNS queries would be encrypted. The adversary won't be able to see the plain text domain names. And we consider a single tab browsing scenario for simplicity purposes. Now, it is possible to fingerprint multi-tab browsing scenarios with some machine learning techniques, but we choose not to do it because of the simplicity reasons. And we also assume that the on-path observer will not be using any of the flow level features or TLS fingerprints or any timing patterns. The adversary simply relies on the destination IP addresses of the outgoing packets, not even the order of them. So, in order to come up with our dataset of target websites, we merged Tranco top 1 million and Cloudflare Radar top 1 million. We end up with 1.3 million unique websites, and we further filter them out on the basis of their IPv6 availability. We check for a valid quad A record of the primary domain of that website or any of these public resolvers. And if it is available over IPv6, we classify it as IPv6 website. So since our adversary is regionally co-located with the victim and it is local to the victim, we use one vantage point and all our crawlers are in the same network. Each crawler takes a website from the dataset, crawls it using a browser, logs the har file, and extracts all the domains out of it. So our crawling process was done in batches over the course of 3 months. We had in total of 5 crawl batches. Each crawl batch was initiated 15 days apart from each other, and approximately each crawl batch lasted for 1 month at least. So, in total, at the end of our experiment, we visited each website 5 times in total. For active DNS measurement of all of the 850K domains that we see while crawling the websites, we do hourly DNS queries in a round robin fashion across all of these public, encrypted public DNS resolvers. So, moving on to the methodology, we selected the dataset of websites, we crawled them, and now we build a high level domain based fingerprint. Now, if in case of in case of the absence of domain name encryption, that was it. That's what we needed to do. But since domain names are not visible anymore, we so yeah, so this is how the domain based fingerprint looks like. We have DP, which is the primary domain or the fully qualified domain name of the website. And we have DS, which are all the secondary domains that the website uses to fetch the resources from. And it is to note that we don't consider the order of these domain names because the order depends on a couple of more dependencies, such as network config, browser caching, and stuff like that. And this is an example of how a domain based fingerprint looks like. So, using these domain based fingerprints and the active DNS measurement that we did, we form IP based fingerprints. So, for each website, we build 2 versions of it: IPv4 fingerprint and IPv6 fingerprint. IPv4 fingerprint has all the records of the domain names, and for IPv6 fingerprint, we try to resolve each domain to its IPv6 address, but if it's not available over IPv6, we fall back to IPv4 following the dual stack nature of internet. Here's a distribution of the percentage of resources fetched over IPv6 by each website. We have 32% of websites that fetch all of their resources over IPv6. 7% websites don't fetch any resource at all, but we still classify them as IPv6 website. And there are 2% of websites that just have their landing page hosted on IPv6. So, on the basis of this distribution, we classify our dataset into 2 subcategories: pure IPv6 sites, which are the websites that fetch all of their resources over IPv6, and also the websites that don't fetch any of the resources, but their primary domain is available over IPv6. The next one is mixed sites. These are all the sites. These are the sites that fetch partially some of their resources over IPv4. So once we have IP-based fingerprints, we move to testing. And for matching purposes, we employ the technique of information entropy. So if a domain appears to be if a domain appears in almost all of the websites, it is a weak identifier for us. So it must have low entropy. And if a domain rarely appears in a couple of websites, this will be a strong identifier for us, and it will have high entropy. And PD here is the probability of a domain being contacted while visiting a given website. In order to calculate the entropy of IP addresses, because domain names are not visible, we take the average entropy of the domains that the IP address is seen hosting. So here's a CDF plot for the domains IPv4 and IPv6 addresses. We see that domains are most distinctive as we expected because there is no sharing of domains as such. But we see that IPv6 has a major percentage of IPv6 addresses have high entropies, and the IPv4 comes after that. So once we have matched our fingerprints, we repeat this process again and again to see the robustness and stability of this fingerprinting. So here we have the percentage of accurately identified websites in each of the categories, mixed sites and pure IPv6 sites for each of the protocol. We were able to identify 93% of websites. So we see high accuracies for mixed IPv4 and v6 sites. And the difference between these two protocols is negligible. And for pure IPv6 sites, the accuracy significantly drops, which is quite unexpected to what the entropies were pointing to. And we also see that the difference between IPv4 and IPv6 for pure IPv6 sites is quite huge. So we further explore this to find out the reason. The effectiveness of a fingerprint is dependent on how unique that fingerprint is as compared to other websites. So in order to visualize that, we plot a probability density graph of Jaccard similarity of each website's fingerprint with every other website's fingerprint. And we plot the non-zero similarity pairs in this probability distribution. For mixed sites, we see that there's almost no overlap between the sites, which is why we were getting high accuracies for mixed sites. And you can see that it's a highly heterogeneous deployment where each website is deployed on a distinct prefix of provider. And for pure IPv6 sites, we see a multi-model pattern. We have a couple of high similarity websites, website pairs, and an evenly distributed moderate overlap. The conclusion from this is that pure IPv6 sites share larger provider prefixes, which creates tight clusters, and it becomes really difficult for the classifier to distinguish between the fingerprints. But why was entropy pointing towards the opposite trend? Like, why was there a concern? Why was there this concern in the community that things are bad in IPv6? So we see that throughout and throughout the measurement period, we keep discovering newer and newer IPv6 addresses that were because of the high churn rates. But for IPv4, it just dies down after some time. We don't get to see new IP addresses for v4. The entropy plots that the community was plotting or that we just plotted, the entropy is inflated by these huge number of newly discovered IPv6 addresses, and this creates this illusion of uniqueness, which is not the case. So, in order to demystify that, we come up with this realized information gain, which only uses the entropy of the IP addresses that are actually used in fingerprint testing. And clearly, we see that 40% of IPv6 addresses are less distinctive than IPv4. And that's the reason why we were seeing relatively lower accuracies for pure IPv6 websites. Fingerprinting, now that we have known that there is high collocation degrees of domains, so fingerprinting risk largely depends on how hosting providers are deploying IPv6 or v4 rather than the protocol itself. To investigate that further, we plot the collocation degrees of each of the provider, and collocation degree is just the average number of domains hosted on a single IP by a provider. And we see that Google, Fastly, and Cloudflare are one of the leading providers with high collocation degrees, and Amazon sits at the bottom with a collocation degree of just one domain per IP address. Now, to explore further the provider specific trends, we calculate the percentage of websites accurately identified by that is hosted by each provider. And instantly we see a trend for pure IPv6 sites that for providers that have high collocation degrees, such as Google, Fastly, and Cloudflare, we see relatively lower fingerprinting accuracies for them. And for providers with low collocation degrees, we see high fingerprinting accuracy for them. So this becomes pretty clear that provider deployment practices they actually dictate the fingerprintability rather than the protocol design. And we also see that for mixed sites, there is no such predictive trend that we can follow, which points us to the fact that mixed IPv4 and v6 sites, their uniqueness and their fingerprinting effectiveness comes from the IPv4 uniqueness rather than the IPv6 part of it. And for the mitigation part, so IP-based fingerprinting works because domains resolve to stable and predictable IPs. But if we are able to somehow disrupt this mapping, the fingerprinting immediately breaks. So the idea is to introduce as much uncertainty or variability into these assignments and mappings. These are some of the potential strategies that providers may adopt to mitigate this fingerprinting risk. And the most important one is to collocate unrelated sites on some of the pools of addresses. And we also recommend that providers should use server-side prefix rotation, which is not really a renowned thing, but we see here that around 80% of the domains that we saw in our study, they all had less than 10 unique prefix, less than 10 unique prefixes that we saw for them. So this is something that they really need to keep in mind. So the pros of these strategies is that it becomes really harder for adversaries to fingerprint websites, but the cons are that it adds another layer of complexity for DNS, load balancing, and network configuration. So providers really need to come up with a balance between all of this. That is it from my side.
Thank you, Sumeer. Questions?
Thank you very much for the talk. I have a question for the collocation, like the table you had at the end with Google. So that means Google is using the same IPs for many of the services. Is that correct?
So this means that Google, on average, hosts 65 domains per IP address.
Okay. And I guess in this measurement are from a single vantage point.
This was a single vantage point.
And I see that for Google that if I ask google.com in Tokyo or google.com in Barcelona, I got completely different IP addresses. But still, like they probably collocate like domains regionally. How to say that like I might be served like 65 different domains for the same IP I see in Tokyo. Yeah. So does it mean it's even harder to fingerprint because those IP also depends on the location where you are? Right?
I think it's a very location-specific behavior. You cannot really generalize it to anywhere on Earth. But in this case, it will be really harder to fingerprint the domains that are hosted on Google with this collocation degree.
Okay. And another thing I see with Google is that they rotate their IPs. So every 2 weeks or so, like I see like my google.com is then a different IP. So I was wondering if you looked into that or if there like
I did not look into the rotation of specific providers, but here's this plot. So 60% of the domains had no IP churn rate throughout the measurement period of 3 months. And even I feel like 40% of the domains had a churn rate of more than 10 hours. So it was not something extraordinary that you could figure out over here.
Thanks.
All right, great work. A question is super simple, and I apologize. I missed a threat model. If I'm the attacker, what I want to find out. I'm not fingerprinting browsers, I'm fingerprinting web servers, but why the information is important? Who wants to find out?
Our threat model, so any entity that is sitting between you and the server and is able to intercept the packets coming out of your device, they can use this information to track the users, track user behaviors, target them with their particular advertisements. And even this technique can be used to censor some content because now you know what websites are being visited. Censorship, targeted advertisement, and user classification, user profiling, these are all the objectives of the adversary in this case.
But I can actually add another point to the threat model, which is connected to my question. In a way, another thing that incidentally you're assessing is the impact of collateral damage when you end up blocking a website. So this is something that's happening now in Spain, and we're working together with Cloudflare to assess this, where basically they're blocking the illegal streaming sites for La Liga soccer matches. And as doing this, they are incidentally blocking a bunch of other sites that share the same IP address. And so in the measurements that you're doing, you're also collecting the data to understand how, let's say, resilient in a way they are to this kind of collateral damage. And we've been talking with Cloudflare about actually doing something similar to this. So we should definitely talk about this to see if we can do some research with them, because it's interesting how it translates over to that as well, where you're solving a privacy problem, But at the same time, you're also solving a resilience problem in that there's the issue of you block one site, one website, and like how many other websites are you bringing down with it? And like how are you tweaking your churning in order to be able to improve the resilience or decrease the resilience? How many IPs do you need in your pool? Is it better to use, et cetera, et cetera? I don't know, maybe future work.
Yeah, for sure. I feel blocking IP addresses would always result in overblocking, but if certain specific traffic patterns can be observed and the blocking behavior is triggered by that specific pattern, I think that won't have much of an impact on other services. If you see a combination of IP addresses rather than straight away blocking an IP address as soon as you see it.
So the last question, and I hope it makes sense. Have you looked at flipping it by looking at trackers or tracker domains? So, for example, do tracker domains use more unique IP addresses? Or if you apply ad blocking and you reduce the set of host names that the browser use contacts for one website, how that would affect?
So trackers and tracker domains or advertisement domains, these are the domains that there's a high chance that they would occur in a lot of websites, not just one or two. So these domains are of no importance to us because they don't really provide us with any of the distinction quality that we are looking for. So if there is a very specific domain, let's say abc.com, that we just see in one particular website, and then there is googletrackers.com that we see for all of the websites. So as soon as you see abc.com, you'll know for sure that this particular website is being visited, but you can never be sure by looking at googletrackers.com which website was being visited. And for the blocking part of it, there is previous research done on it where, so even if you filter out all of these trackers and advertisement domains, and since they were of no use to us, even if they get blocked, so it doesn't really matter. The accuracies would still be comparable.
Thank you very much, Sumeer, again.